Welcome back, everyone. Last time we introduced the fascinating world of chemical processes. Today we are exploring the energy story of chemical reactions. So let's start with the fundamental truth. Chemical bonds are like molecular relationships. And just like human relationships, they involve emotional energy. Breaking up any relationship requires energy input. Think about the effort it takes to end a friendship or separate Velcro. In chemistry, breaking bonds always requires energy input, making it endothermic at the molecular level. But here's the beautiful part. Forming new bonds releases energy. Just like the joy of making new friends, when atoms find their perfect partners and form new bonds, they release energy. It's exothermic. The overall energy change of a reaction depends on this cosmic balance. How much energy did we spend breaking up old relationships versus how much energy we got back from forming new ones? Now let's talk about enthalpy. Think of it as the heat content of a system, like the thermal energy stored in a molecule. Here's the thing though, we can't measure absolute enthalpy. Just like we can't measure absolute happiness, we can only measure change. That's where delta H comes in. It's a change in enthalpy, the difference in heat content between products and reactants. If delta H is negative, the products have less heat content than the reactants. Energy was released to the surroundings. If delta H is positive, the products have more heat content. Energy was absorbed from the surroundings. Exothermic reactions are the generous friends of chemistry. They give energy away. When delta H is negative, it means the reaction is literally giving heat to the surrounding. These are the reactions that warm your hands, power your car, and keep you cozy by a campfire. Picture this. When methane burns, it releases 890 kilojoules per mole. That's enough energy to power a 100-watt light bulb for about 2.5 hours. The products, carbon dioxide and water, are at a lower energy level than the reactants. It's like rolling a ball downhill. Once it starts, it releases energy naturally. Most combustion reactions are exothermic, which is why fire feels warm. Even the simple reaction of acid and base. When hydrochloric acid meets sodium hydroxide, releases enough heat to warm up the solution. These reactions often happen spontaneously because nature loves to move to lower energy states. Endothermic reactions are the energy consumers. They are like the molecular energy vampires that suck heat from their surroundings. When delta H is positive, the reaction needs continuous energy input to keep going. The products end up at a higher energy level than the reactants, like pushing a ball uphill. The classic example is photosynthesis. Plants absorb massive amounts of solar energy, 2,870 kilojoules per mole, to convert carbon dioxide and water into glucose. Without continuous sunlight, the process stops. That's why plants need light to grow. Another great example is the thermal decomposition of calcium carbonate. Heating limestone to make lime for cement, this process requires continuous heat input, which is why cement production is so energy intensive. Instant cold packs work on this principle too. They contain endothermic reactions that absorb heat from your injured muscle. Let's visualize the energy journey of an exothermic reaction. Imagine you are following a hiking trail that goes up a hill and then down into a valley. The reactants start at a certain energy level. Let's call it base camp. To react, they need to climb an energy hill. This is the activation energy, like climbing to a mountain pass. At the peak is a transition state, the most unstable high energy point, where old bonds are breaking and new bonds are starting to form. It's like being at the top of the roller coaster. Then comes the fun part, the energy plunge. The products end up in the valley, at a much lower energy level than where we started. The difference between the starting point and ending point is our delta H, negative, because we ended up lower than we started. The energy that we released, that's what heats up the surroundings. For endothermic reactions, imagine hiking from a valley up a mountain plateau. The reactants start in the low energy valley, but the products need to end up on the high plateau. Again, there is an activation energy hill to climb, often even steeper than in exothermic reactions. But here is the key difference. After reaching the transition state peak, instead of rolling down into a valley, we end up on a plateau that's higher than where we started. The products have more energy than the reactants. Delta H now is positive. This means we need continuous energy input throughout the reaction, like having someone push us uphill the entire way. Without that energy input, whether it's heat, light, or electricity, the reaction stops. It's like trying to bike uphill without pedaling. You just roll backward. What determines how much energy a reaction will absorb or release? It all comes down to the molecular details. First, bond strength is crucial. Stronger bonds require more energy to break and release more energy when formed. It's like the difference between tearing paper and breaking steel chains. Molecular complexity matters too. More complex molecules have more bonds to consider. It's like comparing the energy needed to deassemble a bicycle versus a car. The physical state also plays a role. Converting liquid water to steam requires additional energy for vaporization, on top of any chemical change. Think of each molecule as having its own energy signature based on its structure. Some molecules are energy rich, like gasoline, while others are energy poor, like carbon dioxide and water. The difference between these signatures determines the energy change of the reaction. To make meaningful comparisons, chemists established standard conditions, kind of like having a reference point for all measurements. Standard conditions are 25 degrees Celsius, 1 atmosphere pressure, 1 molar concentration for solutions, and pure substance in their standard states. It's like having a universal measuring stick. We have different types of standard enthalpies for different processes. Formation enthalpy tells us the energy change when a compound forms from its element. Combustion enthalpy tells us how much energy we get from burning something. Vaporization and fusion enthalpies tell us about phase changes. These standardized values are incredibly useful. They are like having a comprehensive database of molecular energy signatures. Chemical engineers use these values to design everything from power plants to pharmaceutical manufacturing processes. Now for the practical stuff. How do we actually calculate these energy changes? We have three main methods, and they are all based on the same principle. Energy is conserved. Method 1 uses bond energy. We add up all the energy needed to break bonds in reactants, subtract all the energy released when product bonds form. It's like doing molecular accounting. Method 2 uses standard formation enthalpies. We calculate the energy to break reactants down to elements, then add the energy to build products from those same elements. Method 3 uses combustion data, comparing how much energy different substances release when burned. Each method is like taking a different route to the same destination. The beauty is that they all give the same answer because energy conservation is absolute. Here is one of chemistry's most elegant principles, Hess's law. It states that the total enthalpy change for a reaction is independent of the pathway taken. Think of it like this. Whether you drive from New York to Los Angeles via Chicago or via Phoenix, the change in altitude is the same. This is incredibly powerful because it means we can calculate enthalpy changes for reactions that are difficult or impossible to measure directly. We can break complex reactions into simpler steps that we can measure, then add them up like building blocks. For example, if we know that A goes to B with a certain energy change, and B goes to C with another energy change, then we automatically know the energy change from A going directly to C. It's like having a GPS for chemical energetics. Multiple routes, same destination, same overall energy change. Let's see this energy knowledge in action. Those hand warmers you use while skiing, they contain iron powder that rusts rapidly when exposed to air. A highly exothermic process. The energy released by the iron-oxygen reaction keeps your hand toasty for hours. Instant cold packs work the opposite way. They contain ammonium nitrate that dissolves endothermically when mixed with water. The dissolution process absorbs so much heat that the pack becomes cold enough to reduce swelling in an injury. Your metabolism is a complex series of exothermic reactions. Breaking down food molecules releases the energy your cell needs to function. Even your car engine relies on the exothermic combustion of gasoline. Every breath you take involves both exothermic cellular respiration and endothermic processes in your lungs. Understanding reaction energetics isn't just academic, it's crucial for our planet's future. By designing chemical processes that minimize energy input, we reduce our carbon footprint. This means finding exothermic reactions that can drive endothermic ones, capturing waste heat, and developing better catalysts. Green chemistry principles emphasize energy efficiency, using renewable energy sources for endothermic processes, designing reactions that occur at lower temperature, and minimizing energy-intensive separation processes. Some companies are even using waste heat from exothermic reactions to power endothermic ones in the same facility. The future of chemical manufacturing lies in understanding and optimizing these energy flows. It's like designing the most efficient possible factory where every bit of energy is used perfectly. So the energy adventure continues. See you in the next lecture.